Example about line integrals in which we integrated over the arc length given by this unit circle from having s varying between 0 and 2 pi. Well, this is a really easy and nice example in which we already have everything parameterized in terms of arc length, not in terms of the variable t, which is time, right? Which is the usual way. And well, you might recall from that chapter, in particular section 14.4, when we covered arc length, all we had to do in order to get the arc length parameterization, well, we did one big example in class. However, there's other nicer and easier examples in which, well, the number one thing we have to do is find the derivative of that given function, and if the magnitude is equal to 1, well, then that's the arc length parameter, and we just change from t to s just like that. But when it's not, we have to figure out first that we first have to figure out that arc length function and then back substitute in terms of s. Well, so in this case, that arc length function, let's recall what it is, s of t, that was the integral from a to t of the derivative of the vector valued function of u du. Well, actually, to make this simpler, let's make a the lower limit, let's make it a 0. How about that? And well, so we're going to redefine this integral, the integral that we defined over here. We're going to turn this ds into an easier parameter, which is the one that we're used to work with, which is t. So if we take the derivative ds dt, well, that's the derivative of the integral. It's just a function, the absolute value of r prime of t. That's using the second fundamental theorem of calculus, so you integrate and then differentiate again with respect to another variable. And then if we solve for ds, this ds is the absolute, or rather the magnitude of the derivative of r of t dt. And in this case, well, we will not have the need of reparameterizing a function in terms of s to later have to integrate like the previous example. So having a function of t, take the derivative of the vector valued function, find its magnitude, and just reintroduce this. And recall, one thing to recall here is that this is the square root of x prime of t squared plus y prime of t. So you know the drill for this. It's the square root of the sum of the squares of the derivatives, all right? So that's all it is. And well, so that being said, so we can redefine what a line integral is instead of defining it in terms of s, we can define it in terms of t. And notice how in this case we are changing this ds into the magnitude of the derivative dt, and that's in for a function in 2 dimensions, and we have of course its counterpart in 3 dimensions. And well, it's going to work the same, all right? And well, this function that we integrate, that function of xy, these xy are functions of t, and that function of x, y, and z, those x, y, and z are all functions of t. All right. So let's see. And in this case, there's a little condition here. When we evaluate a double integral. Okay, let me write it down. When we had a double integral, dA, where the integrand is a 1, that defined area. When we had a triple integral, dV, and the integrand was a 1, that was volume. And a line integral for which f of xy or f of xy equals 1, that's going to give us only the arc length. All right? Otherwise, if that integrand is something other than just 1, it's a function of t, well, we're going to have a physical interpretation of this later in the section, but I can actually spoil a little bit. It has to do with the work done by some force into moving a particle from the point A to B along the path defined by C. So we're going to look into that later. In the meantime, let's evaluate some integrals. Let's do some examples. And well, this first example, evaluate the integral over C for the function 1 plus x plus y x plus xy squared ds. So notice the that ds is going to be replaced with dt, because we already now have a form to evaluate this in a lot easier way, because otherwise we would have to figure out the arc length function from here, and then that's not something you feel like doing, right? That's going to take forever. And so along this path over the interval 0 to 1. So number 1, r of t is given. R of t, which is t comma 2t, and in this case, well, x equals, this is telling us that x equals to t and y equals to 2t, because these two we will substitute x equals to t wherever we see the x, and this y equals to 2t wherever we see the letter y. That to write an integral only with respect x. I mean in terms of t. So we need the derivative of this vector valued function, r prime of t equals 1 comma 2, but we also need the magnitude of this vector. That's the square root of 1 squared plus 2 squared, which equals the square root of 5. So let's write down this integral. Number 1, this ds right here will become, let me write it as a ds equals the magnitude of the derivative times dt. So the integral of 1 plus x, which in this case is t, times y squared, which is the quantity 2t squared, and I'm going to replace ds with this whole madness here, that is the magnitude of the derivative of the vector, which is the square root of 5, times dt. And let me highlight this just so you can see where is this really coming from. The square root of 5 is the magnitude of the derivative of the vector. Alright? And well, this should result into basic integral. That goes from 0 to 1, because that's the interval that we were given. And that's the integral from 0 to 1 of 1 plus, okay, so 2t quantity squared, that's going to give us a 4t squared times t. That's going to be 4t cubed, and the square root of 5, or how about, well, let me leave it like this, dt, and we can integrate the 1 plus 4t squared. So that's going to be the square root of 5, and that's a t plus t to the 4th, and evaluate it from 0 to 1. And applying fundamental theorem of calculus, upper limit minus lower limit, this should be 2 square root of 5. Alright? So that's our first example of evaluating a line integral, but in this case using the parameter t and not the arc length parameter, because again, we redefine this to do our work a lot easier rather than having to figure out an arc length parameter and then evaluating on that on top of that. Alright? A second example, example number 5, evaluate another line integral. However, we're going to go from the point 1, 0, 0 to negative 1 comma pi, negative 1, 0 pi, along the helix C that is represented by the parametric equations, and in this case cosine t, sine t, and t. Now remember that helix, that it was like a circle going out like in a spiral, right, going upward. So we looked at this before. And well, that from 0 to pi. Well, just to verify this, because sometimes what makes this this type of integrals a little weird sometimes is that, well, we have a lot of information. We have an integral, we have a set of parametric equations, we have an interval, and we also have points. So if you plug in 0 to these three parametric equation, that's going to be cosine 0, which is 1, sine 0, which is 0, and plug in 0, that's 0. And if you plug in pi, so that's cosine pi, that's a negative 1, sine pi, that's 0, and pi is just 5. Right? That's just, sometimes that's just like extra information to throw you off, like, wait, how do I use these points? And in fact, we're not even going to use these points. Okay? So, alright, so let's write down the set of parametric equations. So that's R of t. In vector form, that's cosine t, sine t, and t. And well, the derivative, because we need the derivative of the vector valued function, and that's to find the magnitude and replace the ds with that magnitude dt. So that's a negative sine t cosine t comma 1. And well, let's find the magnitude. And finding the magnitude over here, so that's the square root of negative sine t squared plus cosine t squared plus 1 squared. And in this case, well, that's going to be sine squared t plus cosine squared t plus 1. And well, sine squared plus cosine squared, isn't that 1? And that's the square root of 1 plus 1, which is the square root of 2. And again, coming back to the arc length function, remember how we had to take the magnitude of the derivative of the vector valued function? If the result is 1, well, then this is an arc length function. Otherwise, well, it's not an arc length function. Alright, but well, we're not parameterizing an arc length function. We're just doing this in terms of t. Well, so the integral over c of xy plus z squared ds, that will be, number 1, the integral from 0 to pi, and well, xy, that's cosine times sine, plus z squared, which in this case is simply t squared, and times the magnitude of the derivative, which is root of 2 times dt. And that simply is that a cubed? Oh yes, it's cubed. Thank you. Cubed. And well, after integrating this one, well, we can do a u substitution on the first term because we have the product between sine and cosine. Notice it's reversed, but it's easier to take u equals to sine because its derivative is positive cosine instead of taking u equals cosine, whose derivative is negative sine. That way we don't have to adjust any signs. So in this case, well, that's going to be the square root of 2 sine, or 1/2 sine squared t plus t to the 4th over 4, evaluated from 0 to pi. And well, after doing upper limit minus lower limit, you know, the basic fundamental theorem of calculus, well, I'll just give you the result. That's going to be pi to the 4th power times the square root of 2 divided by 4. So that's the value of this integral. All right. For now, we are defining the value of these integrals as the areas of the curtain generated by that path over some solid in this case, or some surface, in this case xy plus z cubed. All right, we're gonna give this a different meaning later in the section. In the meantime, let's keep doing more examples. Let's do another one. Notice how every example that we're doing has a different presentation. Well, what do they have in common? Well, number one, the integral, and well, in some cases, they're directly giving us a parameterization. In some cases, we will have to figure it out, like example number 6, and then later for example number 7. Alright, so let's evaluate the integral of c over c of x squared plus y squared ds, where c is the path traveling counterclockwise around the circle x squared plus y squared equals to 4. So, notice something whenever you look at an example like this. This circle right here, it's only a coincidence that it's also the function f of xy equals x squared plus y squared. So that doesn't mean it's the same circle. No, it's just, this is actually, well, z equals x squared plus y squared, which is, again, I think this is a circular paraboloid. And we're going to have the circle of radius 4 intersecting on that paraboloid, and we're going to find the area of that current generated by the path. And actually, in this case, from the point 2, 0 to the point 0, 2. Well, again, we have a lot of information here. And in this case, well, the circle x squared plus y squared equals to 4. So that's well, we can represent the circle, the whole circle, but not really the whole circle, only the circle that goes from the point 2, 0 and 0, 2. And notice in this case, direction matters, all right? So it's going to go in this direction. And, well, so we know how to parameterize a circle of radius a. In this case, the radius is 2. And using the counterclockwise orientation, yeah, that's the word I was looking for before. Orientation, so in this case, that's r of t. And that's a 2 cosine t, 2 sine t. If the orientation of the particle went the other way around, counterclockwise, we would reverse the order of the components of this vector valued function. Well, and in this case, this t varies between 0 and pi over 2. That is, the derivative r prime of t equals negative 2 sine t plus 2 cosine t. And, well, let's find the magnitude of this derivative. So that's the square root of negative 2 sine t quantity squared plus 2 cosine t squared. And that equals the square root of 4 sine squared t plus 4 cosine squared t. Alright? Well, if we factor out the 4, we will be left with sine squared plus cosine squared, which is 1. And that's going to give us square root of 4 times 1, which is 2. Alright, so let's evaluate the integral here. So, the integral over c, the integral over c of the function x squared plus y squared ds, number 1, that's the integral from 0 to pi over 2 of the x component squared. However, our x component is 2 cosine plus the y component squared, which is sine, or 2 sine rather, and that's times 2 dt. Alright, again, let me highlight this. This x is right here, which is that one, and this y component 2 sine t That's this y which is replaced with 2 sine t. And well, that's going to be something similar to our radicand here, integral from t, but in this case for an integral. And that's 4 cosine squared t plus 4 sine squared t times 2 dt. And this will be the integral, okay, cosine squared plus sine squared, that's 1, but times 4, well, let me factor out the 4. This gives a 1. 1 times 4, that's 4 times 2, that's 8. Integral from 0 to pi over 2 dt. And then 8t from 0 to pi over 2. And that's 4 pi. Alright. So that's the area of the curtain hanging only in the first octant. Notice in this case we're not really looking at the solid. So we're only looking at the projection in the xy plane to see what's going on, because really what we care is the path and most importantly the direction or the orientation, well, depending on what kind of parameter or parameterized curve do we have. All right. What's next? Oh yes, the next one, example number 7. Evaluate the line integral x squared plus 2y minus z, where c is the line segment from the origin to the point 1, 4, 2. Well, in this case, they're not giving us any r of t. In this case, they're giving us the point, the initial point and the terminal point of a line segment. But well, we already reviewed how to get those parametric equations of a linear function given the 2 points. So let's parameterize. So the point, or rather the vector, well, let's label this as our point P and our point Q. So this will be that's the vector PQ. That's number 1, terminal minus initial, that's 1 minus 0, which is 1, 4 minus 0, which is 4, and 2 minus 0, which is 2. So that's our vector 1, 4, 2. And well, to find the parametric equations, well, again, recall that the x component is the delta x, the y component is the delta y, and the delta z is the z component of this vector. So, to get the parametric equations for these 2 points, for the line segment subtended by these 2 points, so that's going to be x sub t equals to the x component of the vector, which is 1, times t, plus the initial point, or the x in the initial point, which is 0, for the y component of the vector valued function, that's going to be the delta y, which is 4, times t, plus the y value in the initial point, which is 0. C of t will be 2 times t plus 0. That results into t, 4t, and 2t. So that's going to be our vector valued function, and of course this is going to go from 0 to 1. Again, every time we use the initial and the final point, that means we're defining the set of parametric equations to go from 0 to 1. Alright? Well, let's write it in the vector valued function form. That is r of t. And this is t, 4t, 2t. And well, r prime of t the derivative, because we need the derivative to find its magnitude and turn that arc length parameter into a t parameter. So that's 1, 4, and 2. Let's find the magnitude of this. So that's the square root of 1 squared plus 4 squared plus 2 squared. And that's the square root of 21. Alright. So let's go back to the integral. So what do we have? The integral over c of the function x squared plus 2y minus c, or minus z, ds. So number one, okay, so let's replace x with, okay, let me highlight all this, x, y, and z. And that's the integral, the integral of x squared, that is t squared, plus 2y, that is 2 times 4y, minus z, which is 2t, and times the square root of 21. Okay, I'm gonna need more space over here. And that's square root of 21, and then dt. And that is going to go from 0 to 1, because that was the definition for our parametric equations. Again, there's other ways to parameterize a line. If you don't want to parameterize it from 0 to 1, say from 2 to 3, you would have to fix the components. However, that's going to be more complicated, number one, to come up with a set of parametric equations itself, and number two, the integration itself, and then coming up with new limits. But I mean, again, the coolest thing of using the initial and terminal point to parameterize a linear segment is that the integral will always have limits from 0 to 1. And whenever one of the limits is 0, it's something just really big. Alright? Simplifying all this, so that's going to be the integral from 0 to 1. So that's going to be t squared plus, okay, 8y minus 2y, that's a, or no, that's supposed to be a t. 8t minus 2t, that's a 6t, square root of 21, dt. And well, this is just general power rule. And that's square root of 21 t cubed over 3 plus 3t squared, evaluated from 0 to 1, and after doing the evaluation, that should give us the square root of 21, or rather 10 square root of 21 over 3. Alright, of course we can use these line integrals for physical applications like the ones that we did back in Calculus 2 and the ones that we recently did about mass calculation. Remember those double and triple integrals to find the moments of inertia and then divide by the total mass to get the coordinates of the center of the center of mass of either the planar lamina or the solid. Well, depending on the situation, well, we're not going to go double and triple integrals. We're just going to go with linear segments in this case. For example, we have a semicircular wire, well, of the form y equals 16, the square root of 16 minus x squared, where in this case this is the upper semicircle. And well, how do we know it's the upper semicircle? Because we have the positive radical. Otherwise, it would have been the lower semicircle. And that's the mass density. Actually, the mass density is rho of xy equals to 10 minus 2y. And well, so really what we're doing here is that the wire has a maximum density of 10, so that, let me look at this function more closely. But in this case, the density gets reduced or decreases linearly by 2 units from the top of the solid, from the point where the density is the highest. So they're asking us to find the mass of the wire. Well, so number one, so we would have done it the other way using a double integral. However, we can do this using a single integral, and in this case, but in parametric form. So let's draw a Cartesian plane first. Let's draw the upper semicircle. And what else? That's okay, from -4. Oh yeah, -4 to 4, because that's a circle of radius 4. So the equations will be x equals 4 cosine t and y equals 4 sine t. And that goes from 0. And in this case, because we're not covering the entire circle, we're just going to go from 0 to pi. Otherwise, if we had both upper and lower semicircle, well, we would have gone from 0 to pi. Alright, so r of t, which is the parametric equation in vector form, just write down the components for cosine t, for sine t. And find the derivative, because that's going to be part of the line integral. -4 sine t, 4 cosine t, and that's its magnitude will be, as usual, the square root of the sum of the squares of these two components. -4 sine t squared plus 4 cosine t, quantity squared, and that's going to be the square root of 16 sine squared t plus 16 cosine squared t. And well, as usual, we can factor out the 16. That's simply going to give us 16 times 1, because sine squared plus cosine squared, that's an identity, that equals to 1. And the square root of 16, that's a nice number, that equals to 4. Alright, so let's go back to the integral. So the integral to find the mass, the integral to find the mass, that's the line integral of the rho of xy function over the arc length given by, well, some ds. Well, of course, we're doing this using our parameter t. Well, so that's why we did all this setup. So that's the integral from 0 to pi, because that's what this semicircular segment is covering, from 0 to pi, and that's 10 minus 2y. Well, first of all, over c, and then we do the limits. Give me 1 second. ds, and that's the integral from 0 to pi. That's 10 minus 2 times the y component. In this case, well, our function only calls for the y component here. So that's 2 times 4 sine y. Let's highlight just so you can see where is that coming from. And that's 4.
Is it 4 sine t, or will these the y?
That's what I meant, right? Sine t. Yes, thank you. And well, that's going to give us the integral from 0 to pi of 10 minus 8 sine t times 4 dt. Let's keep distributing the 4 to get a cleaner integral here. Integral from 0 to pi. So that's 40 minus 32 sine t dt, which integrates to 40t plus cos 32 cosine t, evaluated from 0 to pi. And after doing the upper and lower limit of integration, that should give us 40t. No, not 40t, actually 4 pi. 4 pi minus 64. Alright? So those were examples in which we evaluated line integrals whenever we had our function as a vector valued function. However, we can evaluate line integrals of vector fields in this case, not about parametric equations in terms of a parameter t. However, okay, we still have some time, I guess.